All right, everybody, hello and welcome to our next topic, which is probability. All right, probability, and we're going to talk about sampling too, sampling at the beginning of this because it's directly related to probability. So, probability is probably a word you've heard before, right? And probability is something that we often associate very closely with statistics, and for good reason. Probability is the cornerstone for inferential statistics. So, remember last time we talked about how we're kind of learning the ingredients for inferential statistics. We're learning central tendency and variability, and probability is really the last piece of that puzzle. So surprisingly, we don't spend a ton of time in this class on probability specifically, but we use probability for just about the entire remainder of the class. It's that powerful in making predictions in statistics. So we're not getting into that yet. We'll talk about hypothesis testing next. That's our next topic. But for now, we're just going to overview what probability is and how it can be useful and the basic calculations for probability. All right, so here we are again, my big head in the way. All right, so first we have a few terms that we want to consider or remind ourselves of. This is where sampling comes into play here. So remember all the way back to our first lecture, we talked about the difference between samples and populations. So a sample is a subset from a population, and it's something that we hope to make an inference about back to the population. So statistics are from samples. Sample statistics include descriptive statistics for a group of people that you studied. But we also need to consider the population. So we have what we call parameters or population parameters. So we don't have statistics for entire populations. We have what we call parameters, which are actual values for an entire population. These are often not known, right? We can think about, hey, if we want to make a statement or a conclusion about women, we probably don't have data for every woman on this earth, right? Some assumptions are being made in the same way that we assume we're working with a normal curve. Because we often are. And the reason that we make these assumptions and predictions is because if we pool enough data and see enough consistency, we start to see more patterns that are a bit more believable, perhaps, that might be true of our population. So we distinguish our population parameters using Greek letters. So for the mean, instead of x bar, we use this Greek letter called mu. For population variance, we use a lowercase sigma. Remember, uppercase sigma is that big one that tells us to sum everything thereafter. And we square it here, of course. And then population standard deviation is just a lowercase sigma. So just a distinction that's a bit important moving forward. And remember that, kind of tying this all together, why do we use samples? Well, we use samples because they often indicate the population. Even if not perfectly, it's usually comparable. So think back to our z-scores, right? Why do we use z-scores to estimate percentiles? Well, because we expect data to fall generally in this way. So we have some examples here where we have all Canadian women and then a small subset of Canadian women. And then all voters compared to a small subset of voters. Voting, of course, is a time where polling and trying to get information from samples is important to predicting election outcomes. So the whole point of research is to be able to make generalizations or predictions beyond your reach, right? Something that we can't reach all of, right? It'd be very hard to reach every voter and gather data on them before they cast a vote. So what we do is we gather samples and make conclusions based on those samples using inferential statistics, which use probability. So something else we're just going to remind ourselves of before we move forward is this idea of random selection or just randomness in general. Randomness is something else that we assume in a lot of our statistics. Even if we aren't acquiring information randomly, we assume that we're acquiring data randomly. So we talked about randomness. Random isn't careless or unexpected. It's truly random, meaning that every single person, thing, phenomena that you're interested in studying has the potential to be a part of your study, or an equal chance of being selected to a condition within your study. So we're going to continue to talk about randomness. When we talk about probability, we're going to ask things like, if you took a random person out of this pool of people, how likely is it that they are X, Y, or Z, right? Or if we roll a dice and have a random outcome, what would we expect those outcomes to be? All right, so let's actually move into talking about probability now. All right, so we're going to talk about basics of probability, and probability works on outcomes and frequencies. So we've heard of frequency before. Frequency is how many times something occurs, and outcomes are results of experiments or studies. So probability is an expected frequency of a particular outcome. An expected frequency of a particular outcome. And we can put this into a formula, which we will take a look at in a moment. But why do we calculate probability beyond just knowing the chance of something happening? Well, we can interpret probability to examine how truthful a statement is. We're going to move into using statistics like confidence intervals. How confident are you that something is true? That's a probability. We can also assess things like error, how likely an error was to occur in any sort of data collection. But again, to reiterate, most importantly, probability is a cornerstone of inferential statistics, meaning that we rely on probability to tell us if our results were expected, unexpected, given the information we already know. All right, given information that's already there, or of conclusions, or theories that are already present. We want to know if our data or our information matches up or is different. Both things are valuable. If our information matches what's already known, it can fortify knowledge. If it's different from what we already know, we might be finding some new knowledge. So that's what probability is good for, right? How do we calculate it? It's actually a pretty simple little calculation here. So we're looking for an outcome, right? A specific outcome. We're going to start with something very simple, which we'll hop over to in a moment. But we determine how many possible successful outcomes there are for what it is that we're looking at investigating. Then we determine the number of all possible outcomes for that set event, and then we divide the successful outcomes by the number of all possible outcomes. So before we move forward here, I think we should give this a try. And then just a note here on reporting probability. Probability is going to come out as a proportion, right? A proportion, a fraction, and something that we're going to ultimately turn into a percentage. So probability is much like many of our statistics, where the probability of something happening can be 0, meaning it's completely unlikely to happen, or the probability can be 1 or 100%, which means that it's absolutely going to happen. So that's how we're going to report probability. And with that, let's hop over to the whiteboard and give a very simple probability a try to put these things in action. All right, so another way that we write out this formula is something like this. We say, okay, P is for probability, and P is going to stick with us for the rest of the class. When we do inferential statistics, we have a P value, which is a probability value. So here we have P, and we're interested in a certain event or outcome. I'm just going to put an A in here, all right? This is just a placeholder. So we're interested in the probability of something, all right? And to figure that out, we need to know the frequency or the number of times, right? N stands for say our sample, right? So sample of how many times that particular outcome can occur. All right, divided by all possible outcomes, all right? Divided by all possible outcomes. So this is just another way to write out that formula that's given on the slides. But let's go ahead and give this some meaning here, okay? So we can have P, let's say that we're interested in flipping a coin, all right? Something we're all familiar with, and a classic probability example. So if we're flipping a coin, all right, there are 2 possible outcomes. Let's stick with a quarter, all right? There's heads or tails if we're going to flip a coin. So say we're interested in the probability or the outcome of getting heads when you flip a coin. All right, so if we fill out the rest of this formula here, what we would need is the number, right, or the possibility for a successful outcome of heads over all possible outcomes, which in this case would be heads or tails, okay? So if we turn this into values, all right, so the probability of getting heads is equal to, there's two sides, right, and one of them is heads, so we have one possible successful outcome, and we have two total outcomes. All right, so now we have this in a fraction, but we don't leave it as a fraction. We turn it into a proportion, okay, or a percent, all right? So it can be reported either way. But this is basically how we would report a probability, all right? We can take the same example for, say, a dice roll, right? Maybe a dice has numbers 1 through 6. We're interested in how likely we are to roll a 2. All right, so the probability of rolling a 2, right, over all possible outcomes, maybe 1 through 6, would be something like P is equal to 1 over 6, right, which equals to 1 or 0.16 or 16%. All right, so just basic probability here, something you maybe do in your head all the time and don't quite think about it, right? We're often interested in the odds of something happening, right? Do we have a 1 in 2 chance, a 1 in 4 chance? This comes up in things like board and video games a lot, right? We have chances of things happening. So let's go ahead and hop back over to the slides and let's consider a few more things here. So that's the basic mechanics of probability, but let's talk a little bit more about what we can do with it. So let's consider a histogram, okay? We did plenty of work with histograms and frequency tables earlier on in the course. So here's a frequency distribution, so shown as a histogram, where we have 50 people all included in this graph. So maybe we're interested in, we have a few other things in here that we're not going to worry about quite yet, our P's and things of that nature. But say that we're interested in randomly selecting somebody from this distribution that scored a 9 or a 10. Well, if we take a look at the frequency table, we can see that we have a frequency of 2 for scores of 9 and only 1 for 10. So we have 3 possible successful outcomes if we randomly select out of these 50 people. We would take 3 over 50, and that would be our probability here. All right, so just thinking about it visually or with the data that we've been using. Okay, so we have a few more considerations here. Probability is not always quite so cut and dry. Sometimes we have multiple options that we're interested in, right? One thing and another. So here we have what we call the multiplication rule or the AND rule. So use multiplication to figure the probability of getting both of 2 or more independent outcomes. Independent outcomes which have no effect on getting the other. So for example, getting a head or a tail flip on a coin is considered independent from getting a heads or a tails on the second flip. All right, your first flip has no bearing on the second, unless you have a trick coin, and then that's no good, right? So here we have it, right? 2 things are less likely to happen together, right? One thing and another. And we'll get to an example of this, but I do want to just show us the formulas here so we have them in mind. So we'll hop back over here once we start applying them. But if we want 2 things to occur at once, our probability is going to be reduced. Multiplication will make sure that those proportions are reduced, meaning that it's less likely to happen if we're indicating we are interested in 2 specific outcomes happening together. And then we have what we call the OR rule or the addition rule. This is when we have 2 mutually exclusive outcomes, meaning that if one outcome happens, the others can't happen, getting one thing or the other. All right, so if we wanted to get a heads or a tails when we're flipping a coin, we would add up those 2 probabilities, right? 0.5 and 0.5. Then we'd have a probability of 1, right? We have perfectly good odds that if we flip a coin, we're going to get heads or tails, unless we get down into specifics, right? And think about everything that could go wrong when we're flipping a coin. But this is our addition or the OR rule. And again, we'll put this all in practice in just a minute here. And then we have one more kind of amendment to this rule. So we have mutually exclusive events. So if one outcome happens, the others can't happen. So think a coin flip, right? You can't simultaneously get heads and tails. But you could say in a deck of cards, simultaneously get one number or queen, right, or face card. And it could simultaneously have a suit as well. So we can combine probabilities in this way. So when two events can be realized at the same time, that means that we have to calculate the probability as if it is non-mutually exclusive. Non-mutually exclusive, meaning that they can happen together. So we have a sort of combination of formulas here. And we're basically subtracting the probability of an overlap of these two groups. So why don't we get to it then? Why don't we hop over to the whiteboard and do some practice here? All right, let's get a fresh new screen here. And let's try this out with some new data. Okay, so let's say, all right, that you are single and ready to mingle, all right? You want to mingle on campus, all right? Maybe not a good example now that we're in the online format, but that's okay. We're going to run with it. We're going to pretend that we'll be on campus soon. So we're going to have a list of qualities, right, or characteristics of people that you're interested in, okay? What are you interested in a person? Then we're going to have the frequency that each of these occur. All right, let's also pretend that you're part of a research methods class and we have this data. All right, we have this data on eligible singles that you're interested in. All right, so the characteristics that we're interested in, let me go ahead and list them off, okay? So as much as we like to ignore it in psychology, okay, attraction, all right? So we'll have attractive. Again, as much as you want to deny it, right? You're not superficial. You don't care about looks. Psychology says otherwise, but we'll let you have it if that's what you want to say. Okay, so attractive. We'll go ahead and put that there. Let's get another maybe controversial one up here. How about wealth? Maybe you're looking for someone who is wealthy. Okay, so I'll say my psychology piece here. Wealth does not equal successful relationships, right? I think we might already know that. But financial clashing does have a significant bearing on relationships, right? So maybe you're interested in someone with a little bit of cash. Maybe that's what you're used to, right? So let's say that you're interested in people who are attractive, people who are wealthy, but let's say that you're also interested in their academic prowess, right? Are they academically successful? So you have some data here as well. You have groups of people who have an A average, all right, a B average, C average, and D average. Okay, so we'll go ahead and include these here. And then we have the frequency that each of these occur in our total group. Let's say that we have an N equal to, and get ready for this, maybe our biggest N to date. Let's say we have an N of 10,000, all right? There's 10,000 eligible singles, and this is what you know about them, all right? You know that out of those 10,000, we have 6,100 who are attractive, 1,700 that are wealthy, 910 with an A average. What do we got here? 2460 with a B average, 5760 with a C average, and 480 with a D average. Okay, so let's, before we get going here, think about this data set here. So some of these events are mutually exclusive, meaning that one can't exist if the other exists. For example, you can't simultaneously have an A average and a B average, right? And in fact, if you add all of these up, all of these averages here, you should get 10,000, right? Because we're accounting for every person's grade point average or grade average in general here. But is it possible to be both attractive and wealthy? I think yes. Is it possible to be wealthy with an A average? I think yes. Is it possible to be attractive with a C average? I also think yes. All right, so we want to think about if these events are exclusive, mutually exclusive, or non-mutually exclusive. But before we worry about that, let's just practice a good old basic probability, okay? So remember, our formula looks something like this. The probability of whatever we're interested in, okay? So I'm going to put A here. So the probability of whatever we're interested in is equal to the number of times that occurs over all possible outcomes. So this n here is going to be our all possible outcomes. And the possible successes here are these. So we're basically assuming, right, or pretending here that you're going to randomly select people out of this group and see how likely you are to find somebody to your specifications. So let's go ahead and start with one event. All right, let's say that at first you're setting your bar low, and the only thing you're interested in is if the person is attractive. Okay, so we're looking for a probability of attractive. Well, we need the possible successful outcomes here, which is going to be this 6100 value. So let's go ahead and put that over all of our possible outcomes. All right, and what do we get? We get something like 0.61 or, all right, if we want to do it in percentages, 61%. All right, those are pretty good odds, right, if this is all you care about. That's not so bad, right? Even at random chance, you're 61% likely to encounter one of these folk, all right? So let's say you want to up the ante a little bit, okay? You don't only want them to be attractive, but you also want them to be wealthy, okay, or well off. So remember, the and rule is our multiplication rule, meaning that if we want both of these things to be true of somebody we select, that's going to decrease our probability. All right, so we're going to do the probability of attractive and, or I'm going to underline and because that has a significant bearing on what we're going to do next. All right, so we want attractive and we want wealthy. All right, so what do? We get the probability of each. We get the probability of one thing occurring, right? We already got this one, right? So we can put that in here, but it looks something like this, right? So it'd be the probability of finding somebody attractive multiplied by the probability of finding somebody wealthy, which is 1,700 over 10,000, okay? So we get something like 0.61 times 0.17, and when we multiply these together, that's going to decrease, right? That's really going to decrease the probability that we find someone to these specifications. Turns into something like this, okay? Down to about 10.4%. All right, 10.4% if we're going to start to get pickier. All right, so that's two events occurring at once, okay? And these are non-mutually exclusive, right? Meaning that someone can be both attractive and wealthy. Let's go ahead and try for looking at some mutually exclusive events. Let's say that you've given up, right? You meet somebody who's attractive and wealthy and it's still not doing it for you because you can't have intelligent conversation, all right? So let's say now you're interested in the probability of finding someone with an A average or, okay, now we're on to or instead of and, or a B average, okay? A average or a B average. So this is going to be equal to the probability of an A average, okay? Plus, all right, plus because or is going to broaden your horizons, right? You're being less picky if you're okay with one thing or the other. Right, so it's going to look something like this. We're going to get the probability of finding somebody with an A average and then the probability of finding somebody with a B average. So let's go ahead and do that. We had, if we hop back over here, we have 910 with an A average, 2460 with a B average. Let's go ahead and get those in here out of our total. All right, total group that we're drawing from here. Oops, let's give me a little space for my plus sign. Then we'll get our 2460 all over 10,000. All right, so this gives us 0.091 plus, I guess we don't need that, plus 0.246. And what does that give us? It gives us something like 0.337 or 33.7%. All right, not too bad if we want somebody of this intellectual or, shall we say, academic prowess, because we all know that grades aren't a direct reflection of intelligence. But here we have it, all right? Maybe you want to make a selection based on this. But now let's try for some non-mutually exclusive events, all right? Non-mutually exclusive events. And we want one thing or the other. So let's say that we want the probability of, say, someone with an A average, or, all right, you've lowered your bar a little bit. You're saying, okay, I'll just go for one thing or the other. A average or attractive, right? You're back to the attractive. You need that. You can't deny that it's important to you. All right, so what do we do here? We have a little bit more of a complex formula here. So let's hop back over to these slides and take a look. All right, this one's a little bit longer. Because what we're doing here is the addition rule again, okay, because we're looking for one thing or the other. But because they're non-mutually exclusive, there can be some overlap between these two things, right? We can have people that are both one and the other of our events. So we have to go to this formula, non-mutually exclusive, because both of these can be realized by the same outcome. I think this card example does a pretty good job of explaining it too, right? If we're familiar with the deck of playing cards, here we have it, right? Red and an ace, both red and an ace. We can have cards that are just red, cards that are just an ace, and they can occur together. So let's go ahead and try calculating this out. All right, let's think about how we would set this up. So we would need P of the A average. Let's see, I got myself a little scrunch there. P of the A average, probability here, plus the P for attractive. I'll just go ahead and abbreviate that. Then we're going to subtract the probability of A average and attraction. Okay. All right, so let's go ahead and give that a shot. Let's give me a little more space here. So the probability of A average, we already got up here, right? That's our 910 over 10,000. Okay, and then we also need our, what else are we getting here? We're getting attractive, right? We already got attractive as well, so we're going to add that in here. 6,100 out of our 10,000, all right, are considered attractive, the data suggests anyway. And then since these are non-mutually exclusive, we need to go ahead and subtract the probability of these two things happening together. All right, so we have kind of an and rule embedded in here where we're going to multiply these two together. Okay. All right, so let's go ahead and work this out here. So we have 0.091. We're going to add 0.61, and we're subtracting a 0.056. Notice that this is relatively small, right? Because if we multiply two proportions together, that's going to give us a smaller value. All right, so if we add this all together, we get something like 0.701, right? If we add this here and then we subtract our 0.056, we get a probability of 0.645 or 64.5%. All right, you've upped your odds a little bit again. Okay, so these are the basic rules of probability, but let's try one more thing just for fun. All right, let's say that you have figured out, you have determined your correct partner, all right? Amidst all of this data, all the people you've met, you've decided what's right for you, all right? And you're not stopping until you meet that right person. So you want to calculate the probability that you're going to meet them in this sea of eligible partners, all right? So we're looking for the probability of, we'll call it your Mr. or Mrs., whatever we want to call it, right, respectively, all right? So you're looking for somebody with an A average or a B average, okay? You decided that's important, academic prowess, success. And let's say that we're also interested and, okay? So we need an A average or a B average and, okay? So we're adding an and in here. Remember, and will mean multiplication for us. And we also need them to be attractive. All right, so we have or, and then and wealthy, all right? So this is what you decided is perfect for you, all right? So we actually figured these before, right? So we got the probability for an A or a B average, all right? That's right here, this 0.337. And we also got the probability for attractive and wealthy, all right? That was one of our first criteria, this 0.104. So if we just follow the probability rules that are suggested by our formula, right, and by our rules here, We can figure this out relatively easily, right? Even though we have lots of criteria in here. This would be equal to something as simple as that 0.337, right, or the probability of an A or a B average. Then we're going to multiply that to the probability of finding somebody attractive and wealthy, which was 0.104. So when we multiply these together, we're going to get an even lower probability, right? Because we're getting choosier and choosier. There are less and less and less possible successful outcomes here. In fact, if we work this out, it looks something like this, or 3.5%, right? But you're not stopping till you find them, right? All right, so that about concludes what we need to discuss about probability. But as previously mentioned, we'll be using probability in practice for the remainder of the course. So conceptually, it will stick with us. But this is where we'll stop with calculating probability. So as always, be in touch if you have any questions on this topic.